Multi-component flash separations are very common to find in chemical plants in which we want to perform an initial extraction to begin separating out our components to obtain our product, or a purified product. And so what I'm going to do in this video is discuss how a chemical engineer would approach a flash drum, and given some kind of operating temperature, how can we find what kind of molar flow rate to expect in our vapor and liquid phases exiting this flash drum. And to begin with, we're dealing with a flash drum in which we're trying to separate 4 species A, B, C, and D. And I'm going to say that they have a feed rate each of 25 moles per second for a grand total of 100 moles per second, which will be equivalent to our feed flow rate F. And given the temperature that we're operating our flash drum at, we'll know the saturation pressure for each of our components that we want to separate. And these are tabulated values you can look up on NIST, for instance, a government website that provides very good, reliable data. And let's say we've done that already, and we've figured that component A will have a saturation pressure of 10,000 megapascals, B has 1,000, C has 1, and D has 0.5 megapascals. And so the first step we're going to take after we've made our table and listed all of the species is begin to define this term called relative volatility. And relative volatility, we can kind of think of it as a ratio of the saturation pressures. So it would be Pi sat divided by P heavy key sat. And heavy key is the component in our table that we've just drawn, in which when we find what our light key is, the light key is the component that is just above the heavy key component when we've arranged it in such a way that our most volatile component is at the top, we get a ratio that is a lot greater than 1. And so what we find, and I've purposely kind of made this obvious, is that we're going to want to make C our heavy component. And the reason for that is because if we calculate the relative volatility down this list, we would get a relative volatility values of 10,000, 10,000 divided by 1, 1,000, which is 1,000 divided by 1, 1, and 0.5. And what you'll note here is that alpha LK HK is a lot greater than 1. So that's good. So it will help us later on if we're going to perform additional calculations such as the Underwood or Fensky relationship if we're working with a distillation column, for instance. But for the sake of this example, this is the first step we take. We've defined what our relative volatility values are. And now we're going to dive a little bit deeper into what the relative volatility really means. And so relative volatility, called alpha I HK, the relative volatility of component I to the heavy key, is equivalent to the ratio of the equilibrium constants for this species. And so we would have K sub I and K sub HK. And going back a little bit further, we know that the equilibrium constants tell us how the vapor mole ratio relates to the liquid mole ratio at equilibrium via the following relationship, where Y sub I, the vapor mole ratio, is equivalent to K sub I times X sub I. So each component I has a unique relation between these two phases. And so if we solve for K here, we find that K sub I is equal to Y sub I over X sub I. And we plug this into our relation like so. We'd have Y sub I over X sub I, quantity divided by Y sub HK divided by X sub HK. And we are going to now define a new term, and I abbreviate it zeta because I can't draw appropriate C's. It's a Greek letter, but I will use the variable zeta to define something referred to as a split fraction. And this split fraction term tells us how much of a component I ends up in the vapor phase relative to how much of component I entered our flash drum in the feed. And what you do is the following. So we can say that zeta sub I divided by 1 minus zeta sub I over zeta sub hk divided by 1 minus quantity zeta sub hk is equivalent to this term that we've just written here. And you cannot explicitly equate y sub I with zeta sub I. They do not have a linear relationship, but if you view a textbook, you can find the derivation that proves this relationship holds. And this should make intuitive sense if you look at it. Zeta sub I is telling us how much of our species I ends up in our vapor phase versus how much of it is going to be in the liquid phase, and this will be proportional to this whole quantity, the quantity as a whole, but not necessarily the individual components. And if we continue this algebra and we now isolate z sub I, what we'll find is that the split fraction of a component I is equivalent to the relative volatility of component I to the heavy key, which we have from the table above, times the split fraction of your heavy key component divided by 1 plus quantity relative volatility of component I to the heavy key minus 1 times and the split fraction, of your heavy key component. And that was very close. And so now that we have defined this term, I'll rewrite it down here. Z sub I is equivalent to alpha I hk times zeta hk. Just try to make this clear. Divided by 1 plus quantity alpha I hk minus 1 times zeta hk. This is the split fraction of component I. And with this information, the next question is, how do you actually evaluate this term? And even if you know the mole ratio of component of your heavy key component in the vapor phase, that's not enough to be able to determine this quantity here. And so what people end up doing is a guess and check method. But before I get to that, I'd like to talk a bit more about why we can't say why is zeta hk not necessarily equal to y hk. And the reason for that is, just think intuitively. We know that, granted, if V sub I is equal to F sub I, if the vapor molar flow rate of component I is equal to F sub I, then Y sub I must, then zeta sub I must be equal to 1. But if you have other species present, that does not mean that Y sub I will also equal 1, because it's not pure anymore. So I just want to make this point because this was a thing that I had a hard time understanding initially. But what you do to actually evaluate what zeta sub hk is hopefully you'll be given this value. But if not, what you do is you first guess a value of zeta sub hk. And we know that zeta sub hk will be some element between 0 and 1. And it's usually a nice place to start at 0.5. You're just making an assumption that 50% of the moles in your feed are going to end up in the vapor. And so I guess we could say let zeta sub hk equal 0.5. with that value, you're going to plug in the alpha I HK terms from the table we drew above, and you're going to evaluate all zeta sub i's. And with these zeta sub i's, we can determine what the vapor and liquid flow rates are as follows. So if we wanted to know what the vapor flow rate of species I is, it would be equivalent to F sub I times zeta sub I, and then do this for all species I. And then finally, that was 0.4. You can do the same for the liquid flow rate of components I, in which case it would be equal to F sub I times 1 minus zeta sub I. So all the stuff that didn't go into your vapor had to go into the liquid. And then you do this for all components I. And finally, check if the mole balance closes. And what I mean by that is if you sum up all of your moles that are exiting your flash and you get a value that is close, then you know that you're getting warmer. And if you change zeta, so final step would be change zeta sub I until the mole balance closes. And so you would increase zeta sub I, you would see if your mole balance is any closer. If it isn't, you would decrease zeta sub I in your next guess, see if you get any closer to closing your mole balance. Like if you end up having 20 more moles totaled, and then you end up having 10 more moles totaled, then you know you need to keep gradually increasing zeta sub HK, and you just repeat this as necessary. And this can be done in Excel by hand, and it will take time to do. And this is what computer modeling programs like Aspen are doing, and you can probably do this quite readily in MATLAB as well once you write a recursive function to just keep iterating until you get a mole balance that can close within 0.001 moles. And this is how chemical engineers of practice are able to determine what the molar flow rate is for some vapor and liquid phase of multi-component separation. And so I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.